Hello, everyone, and thank you for joining us today. We have an exciting presentation called Fiber Reinforced Polymers, a Game Changer for Concrete Longevity and Performance. Our presenter today is Rick Ellingson. Rick is the Business Development Leader for MAPEI's Products for Structural Strengthening line in the United States. His work experience includes 10 years working for manufacturers of fiber reinforced polymer systems, FRP, structural pile jacketing systems, and corrosion mitigation technologies for concrete structures. More importantly, Rick has 4 young children who do not share their dad's passion for concrete repair. Just as a housekeeping item, if you have any questions, please feel free to drop them in the question box, and at the end of the presentation, we'll do a Q&A session where Rick will answer those. All right, Rick, without further ado, if you want to get started.
Thank you, Brianna. Thank you guys for attending and listening to this today. I am a licensed professional engineer. I'm on the ACI 440 and the 239 committees. That's for FRP and ultra high performance concrete. I'm also a voting member of the ICRI 330 Strengthening and Stabilization Committee. I live in beautiful Tucson, Arizona with my wife and 4 kids. So I hope today you'll be able to take some valuable information for upcoming projects that you might have. A little bit about MAPEI. So MAPEI is one of the largest construction chemical manufacturers in the world. We're headquartered globally in Milan, Italy. Our U.S. headquarters is in Deerfield Beach, Florida. We have 24 product lines that over 6,000 products fall into. In MAPEI being an Italian company, it has the Italian culture of producing quality products. If you think of like an Italian car or Italian clothes or handbags, you're always thinking these are kind of top of the line quality. It's a cultural thing. It's the same with MAPEI. We make very high quality products. I work for several manufacturers and contractors, and I don't hear people saying bad things about the quality of MAPEI's products. And for those that don't know the ins and outs of MAPEI and what we produce, a lot of people have seen us through our sponsorship in the sports world. We've done a lot of sponsorship for Tour de France over the years. This year, we're actually the sponsor for the Andretti racing team. So if you're into Formula One racing, keep an eye out for the blue MAPEI car. So here's an outline of what we're going to talk about today. What are fiber reinforced polymers, or FRP? Their properties, some typical applications, some installation and quality control recommendations, design guides, what's the role of the engineer, and how MAPEI assists and comes alongside the engineer in this process. So there's a lot of industries that have been using FRP composites. You think of the sports world with the carbon fiber bicycles and golf clubs, snowboards, hockey sticks. Same with the automotive, like I just mentioned, the Formula One race cars. They're made with carbon shells, very lightweight, very strong. The industry that's done by far the most testing of these materials is the aerospace industry. And I tell people, if you're comfortable flying in a carbon tube at 30,000 feet going 700 miles an hour, you should feel comfortable having these same type of materials used on your local bridges and the buildings you work in. They've also been used for decades in the marine industry. You think of these hulls of boats. They use a fiberglass and a low quality resin, typically a polyester resin. And these boats, they sit in salt water day in, day out for years, and they perform very well. And then it's also used in more harsh chemical environments like septic tanks is one example, where you have the hydrogen sulfide gas, and they use the same type of fibers, but they just change the resin system. So in those resin systems, typically they'll use a vinyl ester instead of a polyester or an epoxy type resin. Now, for the construction industry, there are a couple limitations. One, these materials are expensive relative to traditional materials. You think of what concrete and steel are going to cost way less than these composite materials. And they also have a poor fire endurance, especially the epoxy. So reasons to strengthen your structures. One, maybe you have a change in use. You're transforming a hotel into a hospital, and you're going to have a higher use. Or you think about all these old bridges that were built, and we did not foresee the sizes of the vehicles going over them, or parking garages, and now we have these electric vehicles that weigh considerably more than what they initially were designed for. Sometimes there's design errors. Sometimes there's changes to the code. One great example of this I like to give is the ACI code for concrete columns before 1970. Then they didn't have much details on the ties that went around the columns. They just said, just put it every 12 inch, regardless of the size of the column, regardless of the size of the longitudinal bars. And what happened is the Loma Prieta earthquake, where there was a significant loading and the concrete shell on the columns broke off and those ties opened up. And so the design community came back and said, there's got to be a better way to do this. So now the hooks are determined. There's now a 135-degree hook that kind of goes into the column, and that way, under significant loading, it pinches the hook and keeps it from wanting to open up. And then they've also changed the requirements for the size of those hoop ties, depending on the column size and your longitudinal rebar size. There's also construction errors. This happens quite a bit, and one great example is there's two 9-span bridges being built. The contractor finished the first, and when he was building the second 9-span bridge, the inspector came by and told the contractor, hey, it looks like you're leaving out half the steel on the deck. And the contractor goes, no, I'm doing this the same way I finished the last one. Well, the first inspector and the contractor missed it, and so now you have a brand new 9-span bridge that is built. What do? Well, the engineer knew about FRP and that it can be used to strengthen his new bridge. Another common thing that can happen is a loss of capacity. This typically comes from corrosion of the reinforcing steel. That's the most common cause. Sometimes the steel gets cut or damaged. You think of contractors like a plumbing contractor that doesn't scan the slab and he's cutting through and he severs some bars. You have impact damage, maybe a vehicle hitting the bottom of a girder and exposing some of the steel or the strands. There's fire, natural disasters. They're also used to increase seismic performance. This is one of the main interests early on, is because these materials are very lightweight. You're not adding a lot of dead load to the structure, and you're able to increase the strength of the structure. And then same with blast resistance. A lot of the federal buildings utilized doing an FRP retrofit because they're concerned about a terrorist attack and having like a progressive collapse where a terrorist takes out a column or two and the whole building collapses. And so they use FRP to strengthen that to prevent those progressive collapses. So fiber reinforced polymer, it's a high strength fiber, carbon or glass. And just to compare these, a typical rebar in construction, you have about, say, 60 KSI. The dry fiber strength of these carbon fabrics around 700 KSI, so about 10 times stronger. Now, unfortunately, there's no way to utilize the dry fiber in our projects. We actually have to get it wet with epoxy to adhere it to the structure. And so when you do that, it ends up lowering the strength, but it's still around 210 KSI. I just took an example of MAPEI's kind of middle of the road carbon fabric. So significantly higher tensile strength than the steel. And these fibers are getting saturated in an epoxy matrix. So these fibers are very thin, about 1/25 the size of a human hair. And this epoxy helps transfer the load between the fibers, it protects the fibers, and most importantly, it anchors it to the concrete itself. So some advantages: FRP is very lightweight. It has a very high strength to stiffness ratio. It's non-corrosive. This is one of the miracle properties of it, especially as our existing structures are corroding. By adding additional reinforcement that will not corrode, that's a huge win. It has a very low profile, very thin. Great application on the bottom of parking garages, on the bottom of joists, where you can't add a lot to the cross section because you have trucks driving in there and everything else. There's a fast installation and cure time. Typically, by the time you put it up, 24 hours, the system's cured, your structure's strengthened. And then also very minimal equipment. You don't need heavy equipment. You see a roll of fabric. You see this gentleman just kind of carrying some of this material, buckets of epoxy. So minimal equipment required to do these projects. So some FRP material properties. FRP is linear elastic until it has brittle failure. So when you think of steel, in this graph here on the left, steel has a very nice behavior where it gets up to its yield strength and then it basically yields. And what that does, and why engineers like it, is it gives us a visual indication that something's wrong. So as the steel begins to yield and stretch, we get to see the ceiling or the bridge starting to sag. And so you go, something's wrong. Let's get the people off of it and take a look. FRP does not have that. FRP does have a brittle failure. So although the materials are much stronger than steel, it does have this kind of a negative limitation where it does have brittle failure. Now, the ACI 440 guide, it takes these into consideration so you're not getting to these ultimate values. So a little comparison just between FRP and steel rebar. I took this middle of the road carbon fabric from MAPEI, and you look at the thickness of one layer. Tiered system is going to be 0.0397 inches, so very thin. And if you wanted to calculate the tensile force, you're going to take the area of that fiber times the tensile strength. So on this one, the design strength is about 210 KSI. And so that gives you about 8.3 kips per inch. So in layman terms, that's 8,300 pounds for every single inch of one layer of the fabric. That's basically like one layer of fabric could lift up an F350. Now, if you wanted to compare that to rebar, you're going to take the tensile, same type of equation, the area of the steel times the strength of the steel. So, a number 8 bar, grade 60 steel, 0.79 inches times the 60 KSI is going to be 47 kips. So how many inches of fabric do I need to kind of equal out this, just for comparison? About a 6-inch wide strip is going to give you the same amount of kips as you would get from a number 8 bar. So materials are incredibly strong. So there's fabrics, there's also plates. They have advantages and limitations for both. With the fabric, it wraps around corners, it has larger widths. The material cost is going to be lower, and then you can do some overlap splicing as well. The plates, you're not able to do that. But the plates are factory laminated, so that increases the quality assurance, where you don't have a contractor in the field saturating the fibers and making sure that he's mixing it correctly. This is done in the factory. The plates also have a higher tensile value. So, instead of 200 KSI, you're looking at 400 KSI. It's quicker installation and just generally a cleaner application. You're using less epoxy, less surface prep. So the plates have advantages. The fabrics also have advantages. So kind of to show you the different costs for like upgrading a beam. If you have a 16-inch wide beam, maybe 40 feet long, and you want to do a 50% upgrade in the live load, well, you could go the conventional route and add a couple number 4 bars, form it up, add some grout in there between materials and labor to do that beam. It's probably going to be around $4,000. Now, if you use the fabric, one layer of our lightweight carbon fiber, that's going to add about 8 pounds of dead load. Place that by hand. Materials and labor is going to come out somewhere around $1,800. Now, and if you did the plate, one strip of a 4-inch plate, same amount of dead load, placed by hand, that's going to come out around $1,400. So just so there's different ways to skin the cat, and each project is different, but just kind of in general terms, this is what it looks like, the cost difference for strengthening beams. So MAPEI has a whole suite of FRP type products. We have the fabrics and the plates. We also have these carbon FRP anchors, and then same with these bars. We have carbon bars and glass bars as well. So before you can even consider using FRP on your structure, there's a few things you need to look at. First, you need to make sure that the compressive strength of the concrete is above 2,500 PSI. If it's below that, FRP is not going to be a candidate for your structure. The other thing is the engineer of record is going to need to look at the primary or existing reinforcing that's in the concrete member and make sure that it is above this 1.1 service dead load plus the 0.75 service live load. And the reason for that is If the structure cannot stand with the existing reinforcing in there, we don't want to add a bunch of FRP, because what happens if there's a fire, or what happens if someone comes in and tries to vandalize the FRP and takes a grinder and cuts across these plates on this picture? We don't want the structure to collapse because of that. And so that's one of these equations that needs to be satisfied. So if it can meet the primary reinforcing, but you have additional loading, maybe additional safety loads that are going to be added, FRP is a great candidate. So in regards to FRP and fire, FRP, it has a poor resistance to heat and fire exposure. So typically around 140 to 180 degrees, the epoxy just begins to transition to a softer state, from a cured state to a softer state. They call it the glass transition temperature. ACI says, FRP composite should be considered completely lost in a fire event. Think of, 1,000-degree hydrocarbon fire. You can put different type of fireproofing coatings on there. They're expensive. Some of these cementitious ones, you can add a couple inches. And what that's going to do is it's going to add additional cover to the concrete member so that it will help the steel interaction with the concrete not to be damaged from the fire, and so it can have fire ratings, but the FRP is not going to make it through the fire. So just something to be aware of. So some typical applications for flexural strengthening. This is if you wanted to, you have a uniform load here on the top, you want to increase the bending capacity. On the bottom of this beam, the fibers on the concrete there are going to be at the most extreme tension phase. And so in a situation like that, you put the FRP there. But then think about the top on these areas above the column. If you add a load, it's going to want to sag the opposite way. And so FRP would go on the top. And so you can utilize FRP to address your positive and your negative bending moments. Now, the way ACI approaches flexural strengthening is very similar for reinforced concrete as it is for FRP. So in reinforced concrete, for calculating the moment, you're looking at the area of the steel times the strength of the steel times the distance of the neutral axis from the reinforcing to the reinforcing steel. Similar with the FRP's contribution in this is the area of the fibers times the effective stress of the FRP times the distance to the neutral axis. Now, looking at the neutral axis on this, you can see the FRP is going to be a little farther away than the steel rebars are. So that gives you, that's good. That gives you a little extra moment arm there to help give you a little bump. Now, as it relates to effective strain, the strain level for an FRP system is typically governed by the debonding of the cured system. So in practice, and what research from universities has shown is that the FRP is going to debond before it reaches its ultimate strain. And so the ACI committee derived strain equations to limit the amount of strain that can be utilized. And so we just don't want the manufacturers like MAPEI to be getting callbacks like we put up the FRP and now it's starting to come off. So these strain equations limit that strain. If you look at this equation here, you can see that as the stiffness increases, the likelihood of debonding increases. So N is the number of layers on the bottom there. E sub F, that's the stiffness or the modulus of the FRP, and then T is the thickness of each layer. So the more layers that you're adding, this equation will eventually go to zero. And so, at some point you're not really getting any additional benefit from a calculation perspective. You're just adding to the project cost. So typically around 4 or 5 layers is where this equation hits zero. Another thing is as the compressive strength of the concrete decreases, the F'(C), the likelihood of debonding increases. So that's why we have a minimum of 2,500. If you have higher strength concrete, that's just going to help you. So some typical FRP applications for beams. This is if you want to do some shear strengthening. If you have a load, you're going to have these 45-degree shear cracks coming off the top of the columns here. Normally you would use some stirrups in the beam in this area. Very similar, you use FRP and do a U-wrap around the beam to increase the shear. Now, anchors are also used, especially in these applications for strengthening beams. We've seen that up at the top. That is an area where it just the development length is typically not long enough to develop the strength, and so it'll typically debond right up at the top there. So some of these FRP anchors are used where they'll drill in to the slab above or to the beam, epoxy that hole, and then stick these FRP anchors and fan it out to help increase with that development length and keep it from debonding. So another common application, this is for walls. If you want to do some flexural strengthening on a wall, say this one on the left, you have a load, and on the right side of that wall, it's going to be in tension. So you put the FRP there, and you can do this in strips. We see this a lot with a basement, inside basements that are bowing from the outside soil. They'll go and they'll put these FRP up against the walls. You're not adding anything. You're not losing any space in your garage by doing this. And then here, this picture on the left, or on the right, the wall cantilevered. On this one, the FRP is going to go on the left because as that load pushes, the left side of that wall is going to be in tension and start to bend. And so you put it there. Now, one of the best applications for FRP is when the material is going to be wrapped onto itself. And these are confinement type situations. You think of columns or piles or even pipes. This is, if you're looking at flexural or shear strengthening, you're really depending on the bond between the FRP and the concrete. Now, if the material is getting wrapped on itself, you're not as concerned about the bond. And so ACI says, okay, for flexural shear applications, those are bond critical applications. But for wrapping columns or piles, these are confinement. And so with wrapping these, you can get an increase in the axial capacity. You think like the load's coming down, the column wants to dilate, and the FRP holds it in there. So you can take a 3,000 psi concrete and cause it to act like a 4,500 psi concrete. Another common application, slab and wall openings. Maybe new ducts are being put in, or a new window or door, and you're going to be severing some of the steels. Some of the steel, they can put FRP there to make up for the capacity that's going to be lost from severing those bars. So this is some just strengthening limit, typical ranges. Every project's different depending on the size of your member and the reinforcing that's in there. But for flexural, you're going to be looking at a range between 40 to 100% increase in the strength. Shear 20 to 150, and then axial about 20 to 100% increase. These pictures just kind of show you the existing reinforcing. You add some FRP. It's similar to if you had a tighter spacing on your bars or more bars in there. So I have a few questions for you as the audience, having gone through some of these examples, just to see if you guys are retaining this and grabbing onto this. So this first one, we have a beam, uniform load. We have 4 scenarios. Where would you put the FRP? Would it be on the bottom, number 1? Would it be up at the top? Number 3, it has it showing on the side. And then number 4, has it showing on the side in the middle of the beam going up and down. If you thought number 1 makes sense, that's correct. Now, you could also do number 3, but you're not going to be able to utilize the full benefit of the FRP being farther away and getting a bigger moment arm. And so number 1 is a more efficient use of the FRP. Here's a column. 3 scenarios. You got a load going down. You put FRP on number 1 here on the sides of it. Number 2 kind of wrapped around in confinement. Number 3 is going on the sides, and it looks like there's an anchor going in to the footer there to help it. And so if you looked at this and you go, yeah, number 2, that would be correct. Now, if we took this load instead of going straight down and we turned it and we made it go to the side, then you would look at a situation like number 1 or number 3, because now you want to prevent the column from bending in that direction, and so you want to look at those situations. All right, last one. You have a cantilevered beam here, uniform load on the top, number 1, the top of the beam, number 2 on the sides of the column, number 3, the top of the beam with the anchor going in, or number 4, the bottom. If you thought number 3, that would be correct. The anchor's going in there to kind of prevent it from having that 45-degree shear crack at that interface. So another type of application is these near surface mounted rods. And these are where a saw cut groove gets put into the concrete, it gets filled with epoxy, and then you put your reinforcing member in there. These are great for applications where you're going to have maybe some vehicular traffic, like in a parking garage, maybe in a negative moment region where you needed it to be on the top of the slab or on bridge decks. Because you would be concerned with the abrasion if you just use the fabric on the top. Over time, the tires are going to tear through the epoxy and eventually the fabric. So by embedding it into the concrete member, it's going to help prevent the FRP from getting damaged. So some pre-installation guidelines. One, you want to make sure that you have a surface profile of a CSP of 3. And that ensures that the weak cement paste is going to be removed and kind of opening up the pore structure to help with the bonding of the system. You're also going to want to make sure you inject any cracks. Any cracks larger than 10 mils must be injected. And what we don't want to have is the FRP to have any movement and cause any like micro buckling in the fibers because those cracks weren't injected. If you have any corrosion on your rebar, you're going to want to clean that. You want to coat the steel with a coating. MAPEI has this MAPEI 1K. We have a Plantibond 3C with cementitious or epoxy coatings. You can install anodes, basically add some energy back in to the system from the energy that was lost, the electrons that were lost due to corrosion. You're going to want to make sure the corners are rounded to 3/4 of an inch, and this helps allow for load transfer through the fabric. The concrete moisture, you want this to be below 3 pounds per 1,000 square feet or 80% relative humidity. And then the installation temperature between 40 degrees and 90 degrees. So in some projects where it's much colder than that, or they're doing it in the winter, they'll tarp off the area and they'll add external heat sources. I'm in the southern Arizona where it's very hot, and so there's things that we do for utilizing FRP here where we'll help condition the resin system, whether keeping it cool the night before, like in your hotel room, or even seen people put the resin in ice baths before mixing, because as it gets hotter, the resin is exothermic, and so it's going to heat up, and so you're going to have much less working time. So by keeping it cool, same type of thing with you do with concrete in warmer environments, adding ice, but keeping it cool, you're going to extend that working time. So some installation steps for the MapeWrap fabrics. You're going to apply a primer. You're going to use this epoxy adhesive. This is a thicker epoxy. We have MapeWrap 11 or MapeWrap 12, and these are formulated for different temperature zones. So depending on the temperature of your project site, you're going to want to select the correct one just to make sure that you have the ideal working time for those that are going to be installing the system. And then we have 2 resin systems formulated for if you want to do a wet layup, which is where you are going to be saturating the fibers before you put it onto the concrete. This can be done with a saturating machine where the fibers will roll through a machine. There's a resin bath. It will get it all wet with resin, and it'll squeeze out any excess, and then you roll it onto a PVC tube and take it over to where you need to install it. And then there's the MapeWrap 31. This is a dry layup system where you're going to be putting the fabric on dry. So you put the primer, your epoxy adhesive, and then you'd roll with a nap roller, some 31 resin. You put the fabric, you'd install it dry, and then you go back again with that nap roller and roll another coat of the 31 epoxy on there. And so dry layup is typically cleaner. Some engineers like the wet layup. Some contractors like the dry layup. They both work, and we have systems formulated for both. Now, I will say that I have seen some manufacturers that for FRP, they'll have one resin system for all 3. I personally kind of cringe a little bit at that because They'll have the saturating resin, and they'll use it to prime the surface. And then if they need to thicken it up, they'll add some fumed silica on site. I'm not a fan of contractors taking the role of a chemist and just adding things into a system that's been formulated and there's been structural engineering calculations behind it. And so MAPEI, we have these 3 different resin systems to address having the best bond, that's the low viscosity epoxy, having the right adhesive depending on your temperature zone, and then giving the engineer or the contractor options if they want to do a wet or dry layout. So, place the fabric. Once you get it wet, you'll roll the fabric, removing air bubbles. It's like a ribbed roller. This is the picture in the top right shows. And then you'll apply additional coat of the 21 or 31. You'll broadcast some quartz sand, and then you can paint it or coat it. Typically, an acrylic paint coating is used over the system. Carboplate installation, similar. You'll apply the primer, the adhesive. It goes to the back of the plate and then also to the concrete member that it's going on for, say, the bottom of a beam. And then you're going to adhere it with a smooth hand roller. You'll push it in and squeeze out the epoxy, make sure it's fully bonded. So quality assurance and quality control items. There's this ASTM D3039. This is a tension test. This is where, as a contractor is installing FRP, he'll make witness panels, which is just a 12-inch by 12-inch piece of fabric. We'll put it between 2 pieces of plastic mylar, and that will get sent to the lab. And the lab will take that sample and cut it into little pieces, and then they'll pull it apart. And they're going to measure the modulus, the strength, and the strain. We've seen this can be a common item. Manufacturers, we're not too crazy about it because it becomes more of a test of how well the contractor can make a sample for the lab. If the contractor doesn't squeeze all the resin out and then you have real thick resin, well, it's going to lower your tensile strength value. Same with if the contractor doesn't perfectly align the fibers in one direction, he has some waviness, that's also going to affect it. And so that can become a problem on some projects where if the contractor made some bad samples, you're looking at it going, how do we correct this? A more important test is a bond test. And there's a couple ASTMs for this. This is their ASTM D4541 and ASTM D7522. They both work. 7522 is a little bit more geared toward FRP applications, where the D4541 is more general coating type applications. But you're going to want to make sure that you have 200 psi above that. If you have above 200 psi when you're pulling that off, you pass. And this is done before the application of FRP and then also after the application. So, and then you're going to want to make sure you test this in areas that are kind of a low stress. So like if you are putting up FRP in the bottom of a beam to increase the flexural capacity, you don't want to test it right in the middle of the beam where the moment's going to be the highest. You want to kind of do it on the side. And so that's, common testings that we see. Then there's field inspections. This is, the contractor's going to want to keep written records. There's special inspections. Sometimes the owner will want the manufacturer or an inspector to come out and give periodic or continuous inspection, depending on the project. Another type of quality control test is this ICC evaluation service, it's International Code Council, and they test essentially the resin system. So a lot of these fabrics, the carbon fiber in general, there's only a handful of companies in the world that can manufacture these. And so these systems get put together where we're taking the fibers and these different epoxy systems and we test it all together. And then this ICC does a durability test to make sure that the system that the manufacturer put together is durable. So for quality assurance control, this is a daily inspection. I'm not going to go through all of these, but it's here for your reference if you wanted to pause this recording and look back later. I will say one thing with the delaminations. Sometimes this can happen, and ACI sets aside some acceptance criteria depending on the size and the number of delaminations. If you have small, less than 2 inches, every 10 square feet, that's fine. If you have large ones, they need to be cut out and patched back with a new piece of FRP, and then the mid-sized ones can be repaired by injecting epoxy into the bubble. One thing to note is during the installation, it's always nice to try to install these as the temperature outside is dropping. And that has to do with if there is moisture in the concrete member. As the temperature increases, it's going to cause some vapor drive of the moisture. And if you're putting up FRP and the project continues to get hotter, you can have some of that moisture kind of seeping through and creating some of these little bubbles. And so the temperature is dropping in the evening, that vapor drive is not really going to become that much of an issue. So with everything, there are some limitations and weaknesses. Same with FRP. Fire, I had already talked about. The epoxy does not do well in fire. UV exposure. This is not only this is just epoxies in general. You're going to want to have some type of a coating because it's not going to do well to the ultraviolet rays. It has brittle failure. That's not good in punching shear applications. The fabric will debond if that's what you're trying to avoid, having a punching shear and you're using FRP. That's not the right application. Abrasion. I mentioned with vehicle tires driving over like a fabric, you try to want to avoid that. Years ago, I was working with a grain silo engineer, and we were looking at strengthening some concrete silos, and we were going to put FRP on the inside. And he asked the question, "How does this hold up to soybeans?" And I was like, "I don't know. I think it would be okay." Well, it turns out soybeans are incredibly abrasive. They're like little mechanical gears the way they slide up and down the concrete, and they'll just eat up concrete. And so learning that, I was like, that's the wrong type of application. So we avoided that. But the fabrics don't do well in abrasion. Installation errors. Typically, this is going to come from the surface prep of the concrete and mixing. If you get these right, that's about 90% of it. So you can avoid a lot of the installation errors. Another limitation is if your concrete, does not have those 2,500 psi, it can't be used. And then one for structural engineers, FRP right now, there's design guides. There are no codes. So the ACI 440, this is kind of the prevalent design guide that most people use. Now, this will be getting adopted in code language in 2027 by the IBC. And so I think a lot of structural engineers will be more comfortable designing from a code than a guide. On the right, this is also an AASHTO for bridge girders. There's a design specification for that. So how to specify FRP? This is typically done two different ways. You could do it in-house. This would be prescriptive, where the engineer is going to design the FRP system. He's going to say, this is the number of plies, the width of the plies, and then the direction that the plies need to be installed. And then he'll specify acceptable FRP products that meet these minimum values, the tensile strength of the modulus. And then the contractor takes those and submits the manufacturer's technical data sheet to say, hey, this is what I'd like to use on my project. So we often see this with non-structural applications like confinement of spalls or protection wraps. There's a lot of DOTs that use this confinement of spalls. So if they're repairing concrete, they put it on, and then the spall ends up popping off a few years later. They wanted to avoid that, so they started putting these typically glass FRP over these spall locations, and that helps it from popping off. A lot of DOTs, Illinois, Indiana, Texas, I've seen California, Washington, Massachusetts, Pennsylvania. Another type of application is performance. And this is where the engineer record, he's going to delegate this out to a specific FRP engineer. In these situations, he's going to need to provide a little bit more information. He needs to provide what the strength of the concrete is, the strength of the steel, the dimensions of the member you're looking to strengthen, the existing reinforcing and the layout of that reinforcing, the concrete cover, and then what is the existing capacity and what does he want the ultimate capacity of that member to be. This method of delegating it out is going to remove some liability from the engineer of record. And this is we've seen used on the majority of FRP projects that require some structural upgrades. So the structural analysis phase, this is what the engineer of record is going to do. He's going to be responsible for doing a condition assessment and analysis of the structure. He's a structural engineer. That's what they do. He's going to determine the location and magnitude of the deficiencies. He's going to verify if FRP can be used. Remember that equation we talked about? And then he's going to determine who is responsible for the FRP, whether it's himself or if he's going to delegate it. Now, MAPEI, we're a product manufacturer. We are not a structural engineering design firm. And as such, we are not going to be stamping calculations or stamping drawings. We partner with other firms to do that. And we do work with engineers during the design phase. One thing we have is this MAPEI structural design. This is a cloud-based calculation tool. This is used globally in a lot of MAPEI's subsidiaries. We're going to be bringing this to the U.S. in the near future. We're working out some of the updates to the code right now. But you select the type, whether you're looking at a concrete building or masonry or a timber member, and then what is it? Is it a beam? Is it a column? Is it a slab? And then from there you put in your inputs, and then it will give you a report, and it'll show you what ACI 440 equations it's using as well. And so we work a lot with the design community in this fashion, kind of helping provide them some stuff, but ultimately it will be the structural engineer or the engineer of record that will stamp these or do the design himself. Another tool that we have available on our website, if you go to our the tools section on our website, down the bottom left there, you see the structural strengthening. You click on that, and then we have different types of CAD files, specifications, technical data sheets. You just pick if you're using a fabric or a laminate, and it'll download a little package for you to put in your project. So a few projects to kind of wrap up here. This was a railway pier in Lithuania. They wanted to enhance the bearing capacity and stability, and they couldn't really add a whole lot to the cross section. It's kind of historical in nature. And so they used MAPEI's Carboplate going up and down vertically. You can see those black strips there. And then going around the pier, they used our fabric, because the fabric molds and it goes around corners where the plates, they don't. This is the National University in Mexico City. They use this to strengthen one of the buildings here. And ironically, 20 years ago, I used to compete in Olympic weightlifting and actually stayed here. And now I'm working for the company that is fixing this building, probably from the damage that myself and the other lifters did to it. It's writing your own meal ticket. Here's a project we did. This is in probably the most famous soccer or football team in the world, Real Madrid. This is the stadium that a lot of our Carboplate was used to strengthen. Here's a high-rise building in Canada. They were doing a change of use where they wanted the bottom a couple levels to be used for a very large conference center. And so they used around 22,000 linear feet of our Carboplate for this increase in anticipated loads. Then here's a small one, a private C-shaped horse island in Dubai. You think of just the environmental stresses with the high humidity and the salt. FRP is great because it's non-corrosive. We use some of our fabrics to wrap the columns. We use some of the plates as well to strengthen some of the slabs there. And that's the end of the presentation. I put my contact information here for the U.S. I also copied my Canadian colleague, Malik. Here's her information if you're up in Canada and you have questions. Go ahead and reach out to Malik. And with that, Brittany, if you haven't fallen asleep, I'll give it up to you to ask. We'll see what questions we have.
All right. Thank you, Rick. Great presentation. We did get a few questions. The first being, does MAPEI have a certified contractor training program?
We don't have a certified contractor training program. We do train contractors. I would say it's more of an experience-based program. When you get into certification, that becomes like a legal type document, and it's hard for us to know if a contractor is hiring or losing guys that were trained on the system if they're all still certified. So we do provide letters of experience. We look at how many projects they've done, and we also get involved in helping the initial project, making sure that the surface prep's done right and the installation. And so we do provide letters of experience, but not certification.
Great. All right. Next question. Can FRP be applied on underwater concrete piles?
I have seen this used. They have different types of resin systems that have a little less washout, and they'll wrap it on the underwater, like a pile or a concrete column, and then they'll wrap it with plastic to try to hold the resin system in there during the curing phase. That can be done.
Great. We got a few more here. Next, do you have engineers that will design and stamp calculations for MAPEI's products?
We do have engineers, but they will not stamp designs and calculations. Like I said, MAPEI is a manufacturer of products. We're not a design firm, and so we try to stay in our lane in that regard. But we do partner with some of the best FRP engineers in the business, and so we pull them alongside. And if you need a stamped design or calculation, we would just put you in touch, and you'd have a third-party design with MAPEI's system.
Awesome. That's great to know. The next question is carbon or glass FRP better for seismic applications?
Good question. That is going to depend. So in a seismic application, you're kind of waiting for the loads to hit. So in some members, you would look at using, depending on the loads that are anticipated from a seismic event, you want to use carbon. Others, glass. I mean, glass is cheaper. It does also have a higher elongation, so it's a little bit more stretchy. And so that's one of the things that typically in a seismic event you'd want to have a little bit more give. So we've seen both in seismic applications.
All right, just two more questions left. Can FRP be used to strengthen steel I-beams?
We have seen that used, whether it's the fabrics or the plates. One thing to be careful with if you're using carbon to do that, is you don't want the actual carbon fibers to be in touch with the steel itself. It can induce galvanic corrosion, so this can be accomplished by utilizing kind of a thick layer of that epoxy adhesive, which is typically done. I've seen others where they'll use a dielectric barrier between the steel and the carbon fiber, like a glass scrim or a glass fabric, and then they'll put the carbon on just to make sure that that carbon fiber, when the contractor's putting it on, does not get into contact with the steel itself and induce galvanic corrosion.
Great. So last but certainly not least, for structural repairs, any considerations for electrical conductivity with respect to old concrete?
Yeah, so like I mentioned, galvanic corrosion, if the steel is in contact with the carbon, carbon is electrically conductive. And so if you're going to be doing a project that, like, say, an electrical substation, where that would be a concern, the conductivity, you'd want to look at utilizing a glass type system, FRP system.
Awesome. Thank you, Rick. And again, everyone, if you have any other questions that might pop up at the end of this presentation in the coming days, feel free to reach out to Rick at the email address on the screen or his Canadian colleague. Thank you so much, Rick, and thank you everyone who attended today.
Thank you.